We're still at the introduction part. I want to explain a few other cases so you understand the purpose of time series. A dynamical system simply has some sort of input. Of course, it could have a bunch of inputs. I'll call it system for now. And as I mentioned at the beginning, even though this is a dynamical system, fully deterministic if you use differential equations and such, by all means, nothing in life is deterministic. There is a random component, so there is variability. In other words, there is noise. Yes. Noise can be explained in terms of probability theory as distribution, right? If you take, I didn't mention this last time, the simplest case of noise. One is what NRA loves. That's the hit. And I hate. Not just because it's more jumps, but it's not that great to deal with. No. Four-letter word starts with S, ends with T.
Short noise.
Short noise. Right. Short noise is the song typically. What is the other one? Awful movie. Did we watch it?
White noise.
White noise. So white noise, you're all young, but if you heard stories of your grandfather, even from your family, back then when we had antennas and stuff, do we remember anyone? No. Televisions, you don't get a proper signal, you'll just see a bunch of black and white dots and a hiss. That's all you get. That's simple white noise. Gaussian noise. So even though you have a system that produces an input, you get an output. There has to be some noise that gets added to it. In probabilistic sense, this could be Gaussian simple terms, normal, 0, sigma squared, 1 would be typical for white noise. That gets added, so whatever YT that you observe is not an exact value, rather it has variability. Even if you have, say, your car, for instance, and the accelerator or the fuel injector, it's supposed to work in an exact way. Does it always work in an exact way? No, there is a range within which it works. As long as it works within that range, you're good. Yes? That range is defined by that noise. Sometimes we want to learn about this system. And in order to do that, T would refer to the time. You can predict what would happen over time by looking at past responses. So things are slowly moving, and based on past times, you can start estimating values of YT. This estimation of YT isn't going to be accurate. If you look at past values and try to see where YT would end up, assuming you know what's happening in the system. There is noise. Let's take the fuel injector. Variability. The fuel will be the input. based on what that input is, you're looking at previous values and you're predicting how things will perform. Would this be an exact value from the get? No, Joe says no. Why not, Kate?
Because of that variability.
Huh?
Like we have a range, approximately what's gonna go in, but we don't know exactly how much fuel is going in.
Exactly. So we know things have noise, so something's coming out, but we're not making an exact prediction, right? So it's going to take a while for the system to learn. You've got to guide the system to do it. Yes, it's not going to magically start giving you correct values. These days, machine learning has become hype, fad, but things were done a long time ago before AI came along, machine learning came along. They're able to recognize it easily now because of computing power. Has anyone dealt with neural networks? No? Okay. One of the neural networks is called a feed-forward network. A feed-forward network is, what does feed-forward mean? Easy question.
Forward,
You're feeding,
or your feet, something.
it's moving forward. So let's say you have time xt, and then you get another version xt minus 1. Perhaps something is perturbed. Regardless, something's happening. You take that and send it back to the output. Feed forward. Yes? Similar analogy, or not analogy, a similar case would be, instead of going forward, you can go backward. Agreed? So feed forward. Feedback. In terms of machine learning, this would simply be application. At the end of the day, we are trying to make a prediction or come up with a value for YC as exact as possible. One scenario, more advanced cases where you could have a controller, for instance, fuel injector, that's got some sort of a control. And if you can't observe the fuel injector directly, you can observe the controller, how it's behaving, use that to predict the output of the fuel injector. Does that make sense? So in an indirect way, so if you've got a controller, I'm not going to draw it because that deals with advanced stuff. You could have a controller, put this output in there, correct the system, and make a prediction. So that is used in control system theory. Did someone take a class in control system? No, used in electrical engineering. So what are we trying to model in this case? Or from a statistical standpoint, what are we trying to understand? We are trying to understand what's happening in that box, right? We want to learn about that box because ingesting this box is going to give us a good value here. Agreed? That box. very important. If you know the transfer function, you know the output. This goes back to what you learned way back when in algebra. You need to define the function. What is a function? You take input, you get output, they draw it and call that to be f. Yes? In control systems, that's just the system, and it's not as easy as f of x. It's got a lot of things going on. So time theories apply to, a dynamical system where processes are stochastic. We use the term transfer function. When I get to modeling, I'll show you what the transfer functions are. If you plan on getting into PhD, not actual science, cool stuff like statistics and things like that. You will hear the term filter. Filter, system, same thing. Often case we go for a linear filter, so this is, but we could have non-linear filters also. Good so far. Another case of time series then comes statistical process control. Very similar to that. Here you observe the process over time. You observe the process over time, detect for certain changes, and you control accordingly. You might have had an over-ambitious professor such as me in undergraduate starts and might have tried to cover statistical process control, usually the very last chapter in undergraduate text. The concept is quite simple. This is also an application of time series. You are observing something over time. If something goes wrong, you want to know a brief. Easy example, credit cards. Yes. Let's say you make purchases and over time things are going this way. And all of a sudden, that happens. Yes?
Is this your spending or?
Your spending. Your usage, daily usage is going that way. All of a sudden that pops up. What does that tell you? Black Friday. Come again? Black Friday. No, Black Friday. Oh, Black Friday. Okay. Possible. What else?
Could be something wrong.
Okay. Define wrong.
Stolen credit card or
Stolen credit card. Is that what you mean? Fraud. Right? Something happened at this point where suddenly you have a very high charge. Certainly, it is possible that Black Friday you spent a lot. Still, given the trend, something like that happens. Fraud. Yes, this is how banks pick stuff, these days. Let's connect it also to what we learned last time. Is that stationary? No, it was stationary up to a point and things went crazy. Stock market, if you follow S&P 500, Dow Jones Index, those are usually not fully stationary. In a weak sense, they are, but if you look at the fluctuations, it sort of goes up and down. Typically, non-stationary currency. That would be another example. What or how do we determine if something is stationary or not? All of these are cases where we use time series. I say tomato, you say tomato, different fields call it different names, but we're all talking about the same thing. Good, that's it. Going to start with a simple case. A random walk. We all know what walk means. Yes, we all know what random means. And sometimes, colloquially, people call it a drunkard's walk. Let's say I had too much fun one night, and I start right here. I'm trying to get home. Good. Going to take my next step, but the next step that I take is going to have variability. Do you agree? So I'm not going to walk a straight line because I've had too much fun. So with some probability, I'm going to move left or right to pick one. Left, what amount of variability? Let's say 0 to 2. Pick them. 2, okay. Left, 2. Another. Left or right?
Right, 0.3.
Right, 0.3. Okay, left or right?
Left,
Huh?
keep going left.
Left. I'm not going to. That's what you're trying to do. No. Left, what's the amount? 1. 1, okay.
Right.
Right,
2.
2, okay.
Right,
As a right, what amount?
right 1,
1, okay.
right 1.5.
0.5, okay. I'm not hitting it either. But you get the point, right? Based on the trajectory that I just moved, do you think that's stationary? No, it kind of goes all over the place. So a random walk is a non-stationary process. Time series, stochastic process, same thing. When I asked you questions, each time I asked two things. What are the two unknowns?
Direction and variability.
Direction and variability. So I asked, well, what step should I take? Forward, backward. Here we went left, right, same thing. And we want to introduce variability. My current step depended on the previous step, agreed? So let's just say X to be the step that I'm about to take. X at time t. would equal to any thoughts? Think of how we did this.
Xt minus one.
Very good. Xt minus 1. Is that all?
Plus epsilon.
Very good. Plus epsilon. I believe your book called epsilon as asymptotic. Textbooks vary, but do keep in mind that they are the same. So epsilon t is going to have some sort of distribution. Let's just say typical normal distribution. 0 has a variance, sigma squared. In my case, sigma was square root of t. That's it. Sigma squared to be 2 between 0 and 2. That is a simple quantum walk. That is a time series. Good. Whatever values that I observe is dependent on one step, one previous step. So that is order 1. Depends on one previous step. Next question, or next thing to determine, what should we call it? What does that remind you of? I'll give you a hint. Let's just say x of t is y, x of t minus 1 is just x. We have y equals x plus epsilon t,
Y equals mx plus b.
y equals mx plus b. In statistics,
Linear function.
a linear function getting closer. Very good. Linear regression, simply a linear walk. In this case, though, even though it is a linear function or linear relationship, that value is depending on itself. Yes? Previous time step, but on itself. So there is a regression, but on itself, hence, we call it auto-regressive model. But makes it fun. Or we're doing sort of regression, auto-regression. Auto-regression, we call it AR. AR automatically implies auto-regression, order 1. I don't want to write it yet. Look at it.
What is the one thing again?
The order. So current step is dependent on one previous step. So order 1. If it depends on 2 previous steps, order 2, and so on. Yeah. Okay. So random walk, and if someone asked you to predict my trajectory on where I'm going, do you think you'll be able to? In a random walk? No. It's purely random, there's no way for us to come up with a pattern and say, okay, it's going to happen. Eventually I'll converge at my place, but who knows when? No one knows. Useless, but easy to understand. Joe mentioned y equals mx plus b. Linear regression. That's m part. We use the specific notation. Do we remember? What's a linear regression? side note. Y equals, we put x there, x is the predictor, plus noise, epsilon. Something went greater, beta, right? Y equals beta times x. Beta simply is the coefficient that we use to estimate y. Okay, same logic. If I have to introduce something like that, what change should I make now? All I need is a coefficient. Same case. Which ways to write this? I'm going to put 5 for now. It's just a notation, you can change it. Good. Out. Is a general definition of an AR model. So random walk is a specific case. What is that specific case?
Size equal to 1.
Side one is what? But finally, one is important. One is going to determine whether our series is going to be stationary or not. Good. Later, we'll start talking about the unit cell, and we'll know what a unit cell is, hopefully. And where the root lies is going to determine whether we are going to have stationary series or a non-stationary series. So pay close attention to one. In this case, I put in one for side one. I explained why that series is non-stationary, but in practice, one would have to determine whether you're dealing with a stationary series or a non-stationary series. Good so far. Okay, case one. Again, epsilon t, I believe your book calls it a sub t. If I go back and forth, I'm used to epsilon t. And xx, but I believe the book uses zt as x. Same. Different method. Case two. I'm going to give it a name yet. I'll just start with the equation. Let's say noise at time t. Noise at time t minus 1. Some random thing that happened. Noise at time t minus 2. You see where I'm going? all of these noise values come from the same distribution. Normal. Independent, identically distributed. There is no connection between one 80 and 80 minus 1. For now, for this case, let's just assume that. What have we seen the movie series of unfortunate events? Or the book? No? So, here you are, or you know, today, some random person. The person's age is 22. What you are today as a person is getting really philosophical. Simply a bunch of random things that happen to you overnight. No meaning, no purpose whatsoever. Philosophy. Good. And would it just be a sum of those values? What you are today, hypothetically, some might disagree with this, but I see, you know, my life to be a bunch of random things that happened. Of course, I'm not 22. I'd love to be. Series of random events that happened, a linear combination of those explains something about you today. Good. Is it just going to be a sum of values? No, Umar says no. Why?
We usually see coefficients on them.
I need coefficients. Perhaps something happened when you were born, right? God waited in some way. 3 years ago, something else happened, had a different way. And 2 years ago, something happened, and here you are. Something happened to tell you. Okay, so those coefficients are likely to determine what you are today. Good. With me so far. If you are someone who likes to live in the present, then what would this equation be? What you are today, you're living in the moment. Huh?
X of t equals, what do you call that?
Psi sub zero.
Psi sub 0 at.
Okay, that's it. None of that would matter. Then, not going to happen. There's always something. So let's say, well, it's not all. Let's consider. A sub t. A sub t minus 1. Based on what we learned about autoregressive model, if I ask you to take a guess at the order in this case, what is the order? What?
What's your name, brother? Yeah.
Diego.
looking back one step. Bit of that. I'm going to assume a special case, and you can tell me what this reminds you of. Let's say sine 0 is 1/2, sine 1 is 1/2. You can put those in here. What statistic does it remind you of? So if I put in 1/2 there, 1/2 there, common factor 1/2, I can pull that common factor out. What does that look like? 2023.
Maybe like the average of the 18.
Very good. I forgot your name.
Andreas.
Andreas. Simply the average of 80 and 80 minus 1. Do you agree? That's my thing. So in that special case, I simply have the average of 80 and 80 minus 1. So I'm going to give the series a name. Averaging a bunch of things. We are averaging families over time. Yes, we are moving along time, moving over time. So that series is that is a moving average series. Yes. So here it is MA order 1. 1 above is simply a moving average series of order 22. Good. And do not forget that a sub t or a sub I for all values I follows norm 0 sigma squared. And sigma squared will come into action later. Yes.
So technically, is the top one order 22 or 21?
22.
So you're counting the x naught and a naught on that one,
Yes.
but not on the second one.
So we look at the number of lags you go backward. So if you just go one time point backward, lag 1. So you're not indexing or you're not using the naming convention based on our typical index. Rather, we are looking at a lag. So if I go one step back in the past, order 1. 2 steps back in the past, order 2. 22 steps back in the past, order 22. Yes? Good so far? Typically, most textbooks will call AR order P, MA order Q. I'll refer to your textbook and make sure what they use. But most texts, if you Google, it's always ARP, NAQ. Way too complicated to write. Agreed, painful. We want to simplify. We like to be efficient. So, backward operator. Some text, websites might call this as lag operator, lag backward operator in the same. The letter that we use is B. What does B do? Suppose you have x of t. B times x of t would equal to x of t minus 1. Good. Take x of t minus 1, B, apply to x of t minus 1, will give you x_t minus 2. But if I want to be adamant, and I say, well, I don't want to with b x_t minus 1, I simply want to deal with x_t. Going back to the beginning of class, dynamic system part, x_t, y_t. So I want to write this in terms of x_t using b forwards.
Just put, x of t in parentheses, so then put a b in front of that.
B, yes. x_t minus 1 is b times x. It's an operator. Operators follow typical operations that we do in math. So b times b, b squared x. Yes. So do we follow a pattern? Let me just ask you, I want to write x_t minus 3 in terms of b and x_t. Very good. Emily, right? It's coming. I got there on my Sunday. Good. In general, x of t k steps, b raised k times x_t. You might wonder why I'm doing this. All of these details are important. Rewriting it this way matters. You will see soon. I started with single cases of AR and MA. We will deal with higher order cases later. Don't want to write the name yet. So let's operate it here. Backward there. Let's see if we can fill in that blank. Give that notation. Common notation. It is a change, right? Typical change we put triangle. I'll look into looking at the textbook. Some use travel, some inverted travel, standard notation, inverted travel, but we'll see what your book uses. But get the idea, it's a change of some sort. Good? Okay, take a guess. What change are we referring to? Time. Okay, let's throw in X.
Is it changing order?
In other words, Caveman, yes, so change in order, how would you write it? Definitely a change. In calculus, if I wrote delta y, what is delta y?
Change in Y.
Change in y, great. As a formula, how would you write it? I'll give you a hint. So, y2 minus y1, change in x, x2 minus x1. Now that I've given you that bit of information, I want you to use xt, and if I want to know the change, what should that expression be?
tk minus tk minus 1.
Very good. So if I consider x of t, a simple change would be xt minus 1. Yes? Good. One step backwards, subtracting. Move one step backwards, and we found what operation did we do? Easy question. Subtract, another word for subtract. Difference. So it computes a difference. You have to give a name. What would that name be?
Backward difference.
Backward difference operator. These operators matter because eventually when we get to transfer functions, we will be writing expressions using these operators. Again, efficiency. I don't want to write a giant expression. Waste of time. Okay, how do I write that expression in terms of b and xt?
Xt minus pst.
Very good. So this is simply be xt minus b times xt. Good. Have a common factor of xt. Well, have that. Good. Order one, so delta sub 1. If you go back to calculus, you should sort of see as to why we call it order. Yes? First derivative, first order derivative, second derivative, second order derivative. You dealt with differential equations in differential equations. Here, the equations that we deal with are difference equations. That's it, differential, difference. But we are doing the same thing in a way, finding rate of change. Good? Okay. The very first application of time series that I started with, do we remember? I said we want to come up with this. I even used hurricanes as an example. Forecasting. Well, forecasting would mean I have X thing. What am I forecasting? That's for a dynamic.
X2 plus 1.
XT plus 1. Yes. XT plus 2. XT plus 3. If I want to generalize it, I would use a forward operator. F times XT will give you one step forward. F squared XT, 2 steps forward. Extend the idea, so F K times XT. Don't think too much about it. XT plus and as I mentioned last time, typically we do not go too far into the future. Your estimates are not going to be correct. If you Google forecasting and looked at images, let's say you have some series going a stationary way, you stop there and you forecast. You typically have a band of that sort. Pretty much in saying, the farther you go, your variability is just going to widen. So that is good enough. So if you are basing your model, this is a question for you. If whatever today or measurement today is dependent on 3 past values, how far should I go into the future? 3 steps. 4 steps in the past, I go 4 steps in the future. That's the best you could do. Some people might throw in 2 more data points, fine, but 10 more steps in the future, not good. With me? Yes. Wanted to do a simulation. Oh, we can save that for next time. Are we clear with this? I'll start with MA. MA is easier to follow in terms of expression, and then we can go to AI next time. Whatever you are observing, X sub t, it is a average, weighted average. Some random value at time t minus 1, no. Book's notation is z sub t. I'm going to use x, I like x better. That's the only example. There is another. Extended tape. This is used in a scenario such as this. Extra tape. Mu plus sine naught at, sine 1 at minus 1. What is mu? Undergraduate statistics, mu is the notation for the mean. So that is the constant mean part. Some like to call it as level. Last time I said, well, we've got a stationary process, we call it stationary if it wiggles around, wobbles around some constant value, right? That was the definition of stationary. That is the constant level we are referring to. So, in terms of time series modeling, you can remove that mean and add it up later because it is a constant. So if you move the mu to the other side, xt minus mu is equal sine naught 80 plus sine 1 80 minus 1. Fit a model, and once you estimate the values of sine naught sine 1, when you forecast, add that bit back. Good. This part right here, the centered version of the series, is simply x tilde. One of the mistakes I've seen people make is people would model this and subtract the mean and use whatever they have here to do forecast and stop right there. Incorrect. You've got to put that mean back in. Just like u substitution in calculus. Once you have the answer, you replace that u. Same thing. You have to add mu back in. But one other thing, and we'll stop there. I want you to give me an expression for xt, the MA1 case here, in terms of b and at. I don't want negativity, I want to get rid of all the negatives. So I don't like negative things, what should I do? I just want to represent it in terms of a sub t and b. No negative here, no negativity. I'll just write that as is. I would like to remove that negative there using b that we saw earlier. In terms of b. You gave me the answer earlier when we did it with x. Same thing with a now.
Just be sine 1 b.
B times sine 1 at, agreed. So sine 1 b times 80, correct, one step backward. 80 coming, pull that up. last expression is a function of the coefficient sine and backwards operator, so we call that sine of b. Good. This is where I'm going to connect the dots. To where we started at the beginning of class. Box. What goes in as input? Life is a bunch of random events. What went in? X of t or A sub t? Current time is explained by a whole bunch of random events in the past. Think of y equals something times x. A is the input, correct? What is the output? X sub t. What goes in the middle? Sine of b. Sine of b is simply the transfer function of a moving average delta, in this case, plus one. So we see the connection between this and where I started. What we have in the middle is the transfer